Right, so again, it is a highly sensitive technique that can be used to help identify compounds. Sample of only a few milligrams are required. It's useful in identifying unknown materials because the mass spectrum of an unknown sample can be compared with your library or database of known spectra. Okay, and these are kind of the machines. We have that, of course, in our lab. And in the real world, they use it in forensic science to solve crimes. Okay, for example, spectral samples could be compared, for example, to link a suspect to a weapon that has been fired. Yeah. Okay, so criminal analysis basically is an application of mass spectroscopy. Now, the mass spectrometers have been included on board several space probes in space. Okay, in 2005, we had something land on the surface of Titan, a moon of Saturn. Okay, so and that's all you really care about that, but in case you want to know for your information, during that descent towards that surface of that moon, the mass spectrometer analyzed the atmospheric composition at different heights, and it was found that the atmosphere consists mainly of nitrogen and methane CH4. Okay, they also detected argon-40. Very interesting. Anyway, so here we go. Okay, so in the mass spectrometer, okay, so when a compound is analyzed in it, gaseous molecules are bombarded with high-speed electrons from an electron gun. Okay, these knock out some electrons from some of the molecules, creating the molecular ions that you guys already know, which travel to the detector plates. Again, this is your basic equation that we looked at already. And the peak with the highest mass to charge, or MZ ratio, is formed by that molecular ion, and the value of MZ is equal to the relative molecular mass of the compound. Okay? Now, the peak at the highest mass to charge ratio on the mass spectrum is formed by the heaviest ion that passes through that spectrometer. Unless all molecules of the original substance break up, this corresponds to the molecular ion of the sample substance. Okay, so there again, the farthest right, okay, peak like we've been looking at for MZ. Okay, now high resolution mass spectrometry can determine the MZ of a peak to several decimal places. So that can distinguish between compounds that have a very similar relative molecular mass, MR, but different empirical formula. Okay, so to integer values like hexane, C6H14, and pentanol, C5H10 and O, both have an MR of 86. However, using atomic masses to 4 decimal places, the MR of hexane is 86.1106, while the MR of the pentanol is 86.0739. So with a high enough resolution, it is therefore possible to distinguish between the hexane and the pentanol, which are both colorless liquids. Okay, see this example. What is the MC of the molecular iron peak of propan-2O, CH3CHOHCH3, on a high resolution mass spectrophotometer? Okay, so let's just solve this one. Let's show how you work it out. Calculate the M to Z charge. Sorry, let me go back. Okay, this is the equation. MZ is equal to MR divided by +1. Okay, and MZ then will equal to MR. Okay, so calculate empirical formula. Then this one, looks like what we did earlier, right, where we saw that other PowerPoint. So that means that this is like CH3, there's 3 of carbons, okay, and then there's 3 hydrogens here, 1, 2, 3, 4, 5, and then plus the 3, that's 8, okay, so that's, and then there's only 1 O. So that's just a very straightforward empirical formula. Now we calculate MR, okay, so 3 times carbon plus 8 times hydrogen plus 1 times oxygen. This is using, of course, your atomic masses and periodic table, and you get overall 60 over 0.0581. And then, of course, then that's your MZ here. And then, so that's it. That's just so easy, okay? But now, okay, let's do another one. Butanoic acid. Okay, this is just from the periodic table, duh. Okay, let's see butanoic acid. It's 1, 2, 3, 4. H, yeah, O2. So basically all you guys are doing basically is for MR, you're just getting your molecular mass, okay? That's not so hard. Okay, I don't think we need to do all these. Wait, let's see. Oh, this is better, okay. High resolution mass spectrum has a molecular ion peak at 30.0474. What is the sample compound? Okay, so get the MR written down, 30.0474 because they gave you. Substitute the AR values into each formula to see which has the correct MR. Okay, so let's go back here. All right, so C2H6, let's see, is that, C2H4 is that, CH2O is this, C6H14 is this. Yeah, so we have to choose from these options here, okay? So then identify the sample compound then is C2H6. Why? Because that is right there, the closest one, okay? So then we know that this one, the mystery compound is C2H6. Okay. What is the empirical formula of a compound that gives a molecular ion peak at 44.01? So you got to choose from this list, okay? Again, let's get the MR of 44.0011 in 4 decimal places. Now substitute, like get a relative masses of each of these. And so the one that is closest to 44 is N2O. Yeah. There we go. All right, so we got that done. Okay, so what is fragmentation? How can this help identify compounds, right? So when the mass spectrum of a compound is 1, a number of peaks at the lower mass to charge ratio, okay, a number of peaks at lower mass to charge ratio than that of the molecular ion would be observed. There we go. So this is the mass spectrum of a compound with empirical formula C3H6O. So this can be confirmed by the high resolution mass spectroscopy. However, high resolution mass spectroscopy cannot distinguish between, let's say, propanol and propanone, so which both have the formula of C3H6O and which both have an M mass to charge ratio, or rate value of 58. So the molecular ion M plus may split into fragments in a process called the fragmentation, or the other stuff besides the base peak and the M molecular ion peak. So the mass to charge ratio of these fragments can be matched to the peaks on the spectrum at lower mass to charge values. Okay, so for this case, the CH3, CH2, CHO plus, okay, ion can split into fragments in 3 ways. If the bond between the CH3 and the rest of the molecule is broken, 2 fragments may be formed. Okay, one with a mass to charge ratio of 15 and the other with a mass to charge ratio of 43. Okay, and we saw these already that I gave you in the other PowerPoint. If the bond between the CH3, CH2 and the rest of the molecule, okay, is broken, then 2 fragments may be formed, okay, both with the mass charge ratio of 29. Finally, if the bond between the CH3, CH2, CO and the single hydrogen is broken, 2 fragments may be formed, one with a mass to charge ratio of 57 and the other with a mass to charge ratio of just 1. So if the bond between the CH3 and the rest of the CH3CO, CH3 plus ion is broken, wait, let me go back a little bit fast. So, okay, so let me just go a little bit further. Okay, let's pause here a little bit. Okay, so if the bond between the CH3 and the rest of the CH3COs, wow, it's really fast. Sorry, guys. These go by too fast. Okay. All right, so if the bond between the CH3, okay, and the rest of the CH3CO CH3 plus ion is broken, two fragments may be formed, one with an MZ of 15 and the other with an MZ of 43. And these are the same as those that can be formed by the CH3, CH2, CHO plus ion. There we go. Yep, there we go. Broken up to 15 to 43. So the presence of peaks at 29 or 57 in the mass spectrum, right, confirms that the compound is then propanol, because these fragments cannot be created from the propanone. And that's how you apply fragmentation with solving between two compounds that you're not sure of. Okay? Okay, so I was on this show. All right, so what we have here, okay, let's have a look at the spectrum of ethanol, okay, which has the molecular ion, okay, basically CH3, CH2OH plus, which you see here, okay, and then we want to try and interpret the spectrum so that if we had to write the formation of the molecular ion, the formation of the molecular ion, we would get ethanol, okay, and an electron, right, to shoot at it, with the electron gun, and it would form the plus charged CH3, CH2OH plus ion, and of course, 2 electrons over here, right? Now, the molecular ion will be the largest peak in the spectrum. So our M plus is around at 46 here on the spectrum, okay? And our base peak is a peak that has 100% absorbance. So it will be there at 31, okay? Now we need to go through and work out what these other fragments are. So we have a CH3 plus here that has a M to Z, okay, mass to charge ratio of 15. Some of the other things that we can start to work out, okay, let's see. Well, at 46, okay, and going all the way down to 31, that's a loss of 15. So that loss of 15 is, we know, a CH3 group. So if we lost a CH3 group from our ethanol, our base peak, okay, will be then CH2OH, right? Which is obvious here, okay? Because that's what we started with. So we lose the CH3, we have only that part left, which is right there, the CH2OH plus. Got it? Yeah, that would be the tallest peak you see in the entire spectrum. Now, if we have another look at the next peak, we know that a CH3CH2, okay, that weighs around 29, okay? So that would be the peak there, and the peak at 27 here would be a CH3 and a carbon, okay? So that's your CH3C plus peak, right? So then that's just the other fragments that we have. Now, these are some typical fragments that you basically need to remember according to IB, okay? And then this is all kind of where it's summarized right here. So here we go. Loss of 15, loss of CH3 is associated with M value of 15, M value of 17 is loss of OH. At 29, it's CHO or C2H5. At 31, that's loss of CH3O. And at 45, it's loss of COOH, okay? So these are your key fragments. Fragments, we call them M sub R, okay? The R is like whatever number is on here, okay? The MZ ratio. Yeah, I hope that's not too bad there for this slide. Okay, so now, on this one, we're talking about the degree of unsaturation, okay? It's also known as the IHD, or index of hydrogen deficiency, right? So we need to be able to calculate this. I mean, the reason why we care about it is that it gives us a useful clue to the structure, okay, of the molecule once its formula is known. Okay? So, I mean, it doesn't have double bonds, it doesn't have rings. So, so anyways, to calculate the IHD, we use the molecular formula. So we add the number of halogens to the number of hydrogens. Okay, we ignore the number of oxygens, and then we subtract, okay, the number of nitrogens from the number of hydrogens, right? So with the first one, okay, let's do this one first, because I'll explain that a bit better. For C9H16Br2, okay, so the index of hydrogen, so yeah, okay, so let's see, C9H, so the IMD of this would just be C9H18, okay, so we basically had to pretend to add the two BRs to the hydrogens, okay, so the IHD would have been C9H18 if we have the two BRs gone. And of course, the general formula is like, CnH2n plus 2, right? And so in this case, then we have a saturated hydrocarbon. This would be like an alkane in this case. So that means the IDH would then be 0, right? So, okay, so that's that one for part C. Part B, okay, ethanol, C2H5OH. So with that gone as one group, if we ignore the O's, okay, and add H only, okay, so we ignore the O's, right? So we add H, so then it appears that this would have been C2H6, which again would have been an alkane. And then, of course, it's saturated and it's I, yeah, so then it's 0, okay? The degree of unsaturation of IHD is 0. All right, and then the last one, C6H5N, we subtract the number of nitrogens from the hydrogen. So then that would be just C6H4. Okay? And in this case, C6H4 would actually have double bonds, which would make it unsaturated. Okay, so yeah, so that means then if it's saturated, it needs to have 14 hydrogens, or okay, or another 10 hydrogens, one or the other. So we must have a large number then of double bonds in here, meaning it's very unsaturated. Okay, so yeah, if you think about it, we're missing, so we either have 14 hydrogens or we're missing 10 hydrogens. Okay, so we must have a large number of double bonds, like 5 double bonds. So it's definitely, unsaturated. And then that's why the IHD, would not be 0. Yeah, so then that means that you would have 5 double bonds, okay? And that's how you answer for the unsaturated ones. Okay. That should be it. Well, okay, let me think about it. I'm looking at C6H5HN. So, okay, so then that means for each 2 hydrogens, we have 1 double bond, right? So then the molecule would, for each 2 hydrogens would have 1 double bond. That means that the molecule would have 5 double bonds because it would be 10 missing ones, okay? It could be a ring and a double bond. Yeah, but we don't care about that. Just say that we have 5 double bonds, okay? That's your degree of unsaturation. Nah, that should be enough for that one.